Good afternoon. My name is Bandan, and I'm here with Eyal. And we'd like to talk a little bit about some of the work that disappeared. So fast forward. Let's go to first slide. This is to talk about Vhost and some of the work that we have been trying to do to get a kind of, if you will, next generation design into the upstream Linux kernel. And the scope of this talk is not something that we have already done, but rather something that's still work in progress. We don't even know if it might go in. We thought that it's probably a good idea to discuss this with the greater community and find out where we are. This is the layout. We just have a very basic introduction, and then we go through some of the ideas that have been posted as RFCs mostly in the recent few years. And then a major portion of the talk is actually Elvis, which is, I think, some considerable work that has been done on this with regards to this topic. And some of our upstreaming efforts and the corresponding results will follow after that. So this is a slide about paravirtualization. So the basic idea, if I'm pretty sure everyone knows, but just in case, that we don't have to assume that the guest has to be in complete darkness as far as where it is running. Rather, we can actually use it to our advantage. And this actually also lets the host, have a little bit of control over what the guest can do. As obvious, this is still a software emulation, so there are scalability limitations to that. But one of the major outcomes from this idea is Vhost.io. What Vhost is in the kernel is that it's a vHostNet interface, a Vhost.io net interface that is actually implemented inside the kernel. It's not a full-fledged Vhost.io net interface, but it just implements the data part, data plane. And one of the advantages is that this is a much better user space and kernel API, which is leveraging on Vhost.io itself. And so this is a very crappy diagram. I'm sure it's not beautiful at all, but what we are trying to show is that this is the kernel thread, and that's the guest running on top of a KVM. And anytime the guest needs some servicing, it notifies the worker thread in the kernel, and also writes data to the buffers, which are shared between the guest and the kernel worker thread. And then when the worker is done with the servicing, the worker thread is actually the one that's interacting with the network stack, and it updates the buffers and sends a notification again. And so this is all just very basic IO event FTIRQFT is kind of the backbone of KVM guest, kernel guest, and hypervisor interaction. So the design of the current vHost is such that we have one kernel worker per device or per virtq TXRX pair, and that is basically the starting point of why we could have a better design. So it might be the case that we don't really need a dedicated kernel thread for one device. We could probably kind of share responsibilities, as in we can have one kernel thread that actually services a lot of guests, and we don't have to actually kind of tightly couple a virtq pair with a kernel thread. So and that is kind of the basis for all these scalable design RFCs. And ideally, of course, we don't want any modifications in the user space. And so the first I'm going to go to is the one presented in around 2012. This is, so don't go by the slide titles. I just made it up just to look a little bit dramatic, but it's not a convention. So what I meant to say is we have like dedicated kernel workers, Vhost workers, on each CPU course on your system, and we have some kind of a NUMA-aware scheduling on top of it. So if the guest needs servicing, the word queues interact with the NUMA-aware scheduler, and then the request goes to one of the cores, one of the workers below, keeping in mind a NUMA locality. And this was also presented at LPC 2012, and so this is all good, but the question is, in this design, we have like, if you will, always on threads. Each core has a thread, and the question, easy question is, do we really need threads to be running on all the cores of the system? And so using that as a starting point, we can say maybe we don't have to run, don't have to utilize all the cores. Rather, why not have a single thread that's running on a core and shared by multiple guests? And that's what is the next design that was proposed. And it's basically, Elvis is actually, I think, a subset of what Elvis proposes is what I just said, and which is that it proposes that we divide the system into a part which actually takes care of executing the guest, and there's this dedicated I/O cores that only do the vhost work. You could probably think of this as pinned, the vhost worker thread pinned to one specific CPU core on your system, and that's where the vhost worker thread is always running. And I'll let Eyal talk about this a little bit in detail.
Yeah. So the Elvis work itself was already presented in KVM Forum in 2013. So I'm just doing a small recap of what was done in that work, and then Bandan will continue on with the upstreaming effort that we're doing right now. So Elvis, in essence, is taking the cores in the system and dividing them into two groups. One running the VM one running the VMs, and the other one running the VM I/O threads. Okay. So if you divide the system into two groups, the groups which runs the I/O threads can be unified, and we can use a single thread per core, and this thread can run multiple devices. And when you have one core running multiple devices, you can do a lot of things. For example, you can do polling. Okay. So this is one thing that is not currently able to do with the original design, right? Because when you have a dedicated thread for I/O, which runs multiple VMs I/O devices, it makes more sense to try and do some polling. And what polling allows us to do is it allows us to reduce the amount of interrupts in the system. Okay, so currently in the traditional paravirtual I/O design, when a guest wants to notify and send a packet onto the network, it has to exit in order to notify the vhost thread that it has a packet that it wants to send. Okay, and after vhost sent that packet, it has to exit again in order for vhost to notify it. Okay. So the second part was partially solved already in Linux, but the former part of exiting can be solved using polling. All right. Because if you use polling, you don't need the VM to exit and then notify the IO thread that it has packets, the IO thread can poll on the VM state and use it without, and know that there's something to send without exiting. So it reduces exits tremendously, which exits are a major performance penalty. And another thing that another thing that we did in Elvis was doing exitless interrupts, right? Doing only running your threads without causing exits. Okay, and the way we did it was using ELI, exitless interrupt, but ELI is kind of hard to upstream. So today in Vhost there are several components that can change it. We can use the KVM PVOI, which reduces the end of interrupt. When a guest sends a packet and the packet is already sent, then the Vhost has to notify the guest. And now in Vhost we can do it without exiting, without causing an exit. Just notify the guest. And another thing, in Elvis we had like software posted interrupts, and now Intel has a VTD technology which allows for posted interrupts in hardware. So there's special hardware do posted interrupts, and posted interrupts allow us to reduce the exits that are caused when the VM gets a packet, right? When the Vhost wants to notify the guest that it has a new packet, it has to cause a VM exit. So now Bandan will take over explaining the upstreaming effort.
So Elvis proposes a lot of things, and we thought that it's probably a good idea to kind of break it down and start with the most basic, which is figuring out if it's possible, if it's worth it to kind of redesign the Vhost kernel infrastructure that we have right now. And so it's a very small change, as in terms of lines of code. It's around less than 300 lines. And what it does is now we have a dedicated worker that services up to a certain number of guests. The default we have right now is 7. I don't know how he reached that number, but and you could change it. The idea is that if we can stabilize this, then we can add some enhancements like polling on top of it, if it makes sense, that is. And so some of the challenges, there are some challenges with this simple design as well. One of them is C groups. So the way C groups works right now is easy because we have a dedicated kernel worker per device in the user space. So we can just attach to all the C groups that the queuing processor has. But once we are kind of sharing a queue between multiple guests, now that becomes complicated. Either we come up with a mechanism where maybe we kind of keep switching C groups the moment we have something to service, or the easy way, and what we have done right now as a starting point is whenever there's a new device that's been created or a new pair, word queue pair that is being created, we just go through all the C groups that it has, and we look through all the Vhost worker threads that we have created yet, and see if they match. If there's even a single mismatch, then we just create one more. Sounds pretty dumb, but that's what we have right now, and it works. And I think the assumption that I made when we did this is virtual machines or virtual guests are not really regular processes that get killed and get created more often. This is going to just happen once when the guest is created. And this, of course, some minor kind of fix-ups here and there. For example, if there's if the C groups that the user process has is just the root hierarchy in the C groups, then we just ignore the check and we just continue using it. And one of the other problems is with polling. And so what happens if we, at some point in future, introduce polling, and how does it interact with C groups? Do you want to do that?
Yeah. So when you do polling, right, the thread that does the polling has to decide which VMs it wants to service. So it makes sense to integrate C groups into that thread, which introduces some complexity, right? Because if you have so for example, if you want to do polling, you want one thread per core, so you can always do the polling, and you get notified when the VM has a packet to send and stuff like that. And when you integrate C groups into it, and you say that we need to create another thread for every C group mismatch, you very fast go and revert to the old state of having a thread, a dedicated worker thread per VM, right? Because for each mismatch, you've got to create a thread, and that doesn't work well with polling. That assumes that your thread is always scheduled and always running. So we probably need to think about deeper integration of C groups, and we would love to hear if you've got some offers and ideas of how to integrate it.
Okay. Yet another topic is work queues. So the point is, is it possible that we can somehow leverage on the existing work queue mechanism that the kernel has? So I don't know if there's maybe some background for that, is that one of the reasons why work queues or concurrency managed work queues was introduced was a lot of kernel code or drivers ended up using their own work queue mechanisms, and it was thought of that why not have kind of a single kind of backend that everyone can use. So it makes sense for us to think the same as well. And one of the RFCs actually was using work queues instead of having to have our own kernel threads that was doing the Vhost work. But as of now, the biggest problem with work queues is we don't know how to do C groups with that. Even if we do have C groups at some point, the other problem that's going to be with work groups is we don't have much control once the work enters the kernel backend. And so that's going to be the disadvantage. But the advantage, of course, is that we are going to end up with lesser code, and we don't have to worry about a lot of things, as in work queues would be NUMA, where we don't have to worry about that. But this is also something which is kind of an open question. We don't know what to do yet, but as of now, we don't use work queues. We just use our own kernel threads.
Another thing about work queues is that the work queues in Vhost tend to be very small. They're always they're only kept by the number of VMs serviced by the thread, because a VM only notifies you on the first packet or the first work, and then if it has additional work, it doesn't notify you again. So it doesn't add another work to the queue. So the queues are fairly small. So we don't need a big mechanism for it.
You can go through the results.
Okay. So we wanted to show some results, and of course Elvis was already presented in 2013, and we didn't want to show again the same thing. So I'm going to show old results with a new twist, right? So we can see here a net perf TCP stream, which is the performance measurement we had, like the network throughput, and UDPRR for our latency. Okay, and I wanted to add something more, so I added a breakdown. right? So right now we have the blue line, which is Elvis, which is on par with what we presented in the RFCs, right? It's a shared Vhost without polling, without posted interrupt, without nothing, just the shared Vhost. Okay, and then the orange line is Elvis with the shared Vhost and polling. Okay, it polls on the guest. And the yellow line is with polling and posted interrupt. So the yellow line causes no exits. And as you can see, it works the best. And I did like, so I took the former graph, and then I wanted to see how much benefit can we get from using polling and using posted interrupts. And as you can see, for a lower number of VMs, we can get major improvements, right? We get like 35% or something. And when the IO core and when the IO thread becomes more and more saturated, the shared Vhost performs better. And that could be explained by the simple fact that if you handle a queue that produces work, and you don't finish handling all the work in the queue, you just you don't wait for another notification. You just take the thread and you re-queue it and post another work in the shared thread. So you get something similar to polling. So that's why for 5 VMs they're a bit on par, and then for 6 and 7, when the IO thread becomes really saturated, then we can see that using no exits does improve. And for 7, and the yellow line from 6 to 7, we just got line rate. It just got line rate, so it cannot scale anymore. And for latency, because our VMs are always scheduled and the IO core is always polling, we get a major performance boost. Okay.
And so, and finally, we also have 2 graphs with the RFCs that we posted. This was to show the difference between, research and real code. They always have a difference, right? But just the subset of vhost sharing code that we posted upstream as RFC, just using that, let's do some TCP stream and TCP request response. And the results for that are, so it seems kind of I would like to point out that the difference is not that much here, but we don't yet understand why that's happening. So you could see the baseline is the purple line, and the green is the shared vhost performance. And as we increase the number of guests, of course, that's what we want. The performance kind of increases, but it doesn't seem kind of similar to what Eyal just showed in the graphs.
No, but you can see that for like 25 VMs, you get like 30,
yeah, exactly. But
35% improvement.
Right.
So it's still nice.
But the lean, it doesn't seem like that it's actually scaling as as linear as we want it to, right?
Yeah, that's true.
So, and then we also have a request response, but that also, if you see over here is the same thing again. The performance for smaller number of guests somehow shows that baseline is actually better, and even when we increase the number of guests, the performance of shared vhost is better, but it's not as much as we would like it to be. Do you remember your graph about the shared?
Yeah, sure. I have my own graphs, which were done in kernel 3.9, which I can show. No, we don't.
Or don't have it. Okay.
We don't have it.
So that's all we had, I guess. And so the last slide is just summarizing that there's a lot of interesting scope for work, interesting work, and we're going to hopefully slowly make progress towards some solution that's going to be acceptable upstream, and we'll see where it goes.
Yeah. Okay. I can try and show the graphs.
That's fine. We don't have time. Any questions?
Yeah.
No, but we can hear you.
So, can you go back to the last chart you have? Is that, when you're using the shared vhost, is that with polling and?
No, the shared vhost that we posted upstream is not using polling at all. So this is just sharing the vhost thread between multiple guests.
Yeah, and I think the main problem here is that we don't have enough I/O threads.
Oh, yeah.
Yeah.
So Eyal gave me an idea that if we increase the number of dedicated I/O threads for request response and see how that scales with these results, that would be a good thing to try, but we haven't tried that.
Yeah, because those results are fairly new, but we need probably to increase the number of I/O threads, and then you'll see a major, because the original Vhost scheme doesn't scale well in terms of latency. That's something that was shown.
Yeah.
So your baseline numbers for one thread per device, is that all those threads or workers are running on a given core pin?
Oh, yeah. Yes. Let me go back to the, can you go back to the, this one, yeah. So actually up to 10 guests, I don't do anything. I just let it run as your system comes, both for the shared case and the single Vhost worker per device case. But starting from x is equal to 14 here, I start pinning. In the isolated Vhost thread case, I actually pin the cores, pin the Vhost threads once the threads are created, of course, to the core where the guest is running. And for a shared case, I know the Vhost threads are already created when the first guest was created, so I just pin it to specific CPU cores.
Because when we have any serious workload in small packets, with the original design, we have the freedom to basically scale by basically separating that workload.
Yeah,
right now, you're taking that away.
Not really. If you look here, right, there's the baseline, which is the original Virt.io, and there's a baseline with Affinity, where we just, instead of dedicating an I/O core, we take all the threads and dedicate them in one core, okay? Yeah. And as you can see, both of them, both solutions don't scale very well.
You're saying you have 6 cores for 6?
We have 8 cores for up to 7 VMs. So we have 8 cores, and then we have a VM running on each core. And in the case of baseline with Affinity, we just take all the I/O threads and pin them on the 8th core, and that's how we run the system. So it is pinned, and as you can see, it doesn't scale very well.
So that actually brings another topic. We really wanted to have a way of kind of jumping back to the previous design, if possible at all. So, and you can do that if you set the number of guests per worker to 1. It's going to basically be the old design.
Because there's an implication as to how this enters the kernel networking stack. More than likely, you have a tap device and hold that 9-yard after that.
I agree with you. I think it does not, at least at this point, for the RFC version, does not look like something that is going to work for all cases.
Do you have time for one more question?
I guess, yeah.
Okay. So I think currently there is a big limitation to Vhost in that what we observed is that for each of the Vrt.io queues, you have a separate Vhost thread. And particularly when you're dealing with a network-heavy VM, right, which is processing a lot of packets, then the Vhost itself, Vhost thread, kernel thread becomes a bottleneck. Because if you're passing large amount of traffic to a particular VM, then the Vhost uses 100% CPU, each thread. And in a typical network device, you are going to, or network appliance, you are going to have 2 VNICs at least. So you have 2 Vhost threads. So as I said, you are pinning the Vhost threads. So you essentially need minimum of 3 vCPUs just to run one VM, right? Because you need 1 vCPU for the VM, 1 for each of the Vhost threads. So this totally limits the number of VMs that you can create in a particular server. So it will be, it will be useful if the Vhost thread can be optimized, right? Maybe polling is one way, but seriously there has to be some process in that, because there's a big limitation right now with KVM, right? Which we don't see it with ESXi.
Yeah, virtual I/O, from what I've seen, I've been working it for a few years, and I've seen that it does take a lot of CPU especially for 10 gigabits or 40 gigabits, it starts to take.
And unfortunately, we don't have any CPU results with our slides. So yeah, that's a good thing to look at.
Because you cannot pin multiple vertable threads into a single CPU, because already the vertable thread itself is the bottleneck. If you pin multiple of them, then you're going to reduce the performance, right? And you can't. You have to pin, otherwise the performance again goes down.
Yeah.
Yeah, but.
Okay. Thank you very much.